Hello, my name is John Gideon, and I'm a research scientist at Toyota Research Institute. On behalf of my co-authors, Shan and Simon Stent, I'll be presenting our work on unsupervised multi-view gaze representation learning. While the application of large label datasets has greatly improved gaze modeling, the creation of such datasets can be quite time-consuming and expensive. Because of this, there is an increasing interest in learning gaze estimators in a semi- and unsupervised fashion. One recent work that has accomplished this is the gaze cross-encoder, proposed by Shan et al. During last year's ICCV. It works by forming two different types of pairs, a pair taken from different time instances which have a different gaze, and a pair taken from the same time instance but from the left and right eyes. They assume that the gaze should be similar between the left-right pair as long as they are looking at something reasonably far away. Their model explicitly encodes two different representations using a standard ResNet pipeline, one for the eye appearance and one for the gaze. The left-right pair is depicted here. Because the gaze representation should be similar from the two inputs, it's possible to swap the gaze encodings and still be able to reconstruct the original image. This constraint in sampling strategy allows the model to disentangle these two factors. The gaze representation can then be used during few-shot learning to train a gaze estimator with substantially less annotation. Our new approach builds on the cross-encoder in three main ways. I'll first explain how it uses an improved multi-view feature structure, which allows for the head motion and subject characteristics to be separately disentangled. We use four weak assumptions about gaze to reconstruct our representation space. In total, we use 8 views of the eyes, forming a 3D matrix across time, camera view, and the left and right eyes. Such data could be acquired, for example, from a stereo view of a person's face. At train time, we require at least 2 simultaneous camera views to be present. This allows us to keep all other factors constant except for the rotation of the head. Similar to the cross-encoder paper, we use the left and right eyes to capture the impact of eye appearance while keeping all other factors constant, including gaze. We also form views from 2 different instances in time. We constrain this to be a relatively short interval so that the eye motion is more likely to change than the head motion. Because of this, only the representation of the eye motion relative to the head should be changing. Lastly, we observe that all these views have common features related to subject appearance and lighting, and form the common features shown in orange here. For a baseline comparison, we apply these multiple view and feature representations following the cross-encoder methodology. This is shown here for a sample pair with changing camera view and respective head rotation representation. Since all other features should be constant, they are able to be swapped. While this gave us the ability to disentangle head rotation and common features using the standard cross-encoder, we saw that improvements could also be made to the model structure to improve its efficiency, flexibility, and performance. Our pipeline begins by first encoding all 8 views to the 4 feature representations. Due to the similar head rotation, appearance, and relative gaze within certain subsets of views, we expect them to share similar features, depicted here as either light or dark colors within each representation. To enforce this similarity, we then summarize these 4 similar features by taking the mean representation and forming a basis feature. We end up with 2 basis features for each representation, the first and second camera view basis features, the left and right eye appearance basis features, and the first and second time instance relative gaze basis features. We also summarize all common features into one basis feature shown in orange here. Because these basis features span all of the inputs, different permutations can be used to reconstruct each input and enforce an L1 loss. Our model is quite flexible. For example, missing data can be simply handled by ignoring the input when calculating the mean basis features. Furthermore, additional camera views, time instances, and view patches, for example, full-face inputs, can be easily added as additional basis features for a particular representation space. The model is also more efficient, taking around half the time to train versus a comparable cross-encoder. One final improvement we make to our model is to modify the formation of basis features to obtain a measure of confidence for each view. The originally introduced summary function simply takes a mean of the representations to form a basis feature, here shown for just one camera view. However, this may not be ideal if one input view is corrupted or obscured. To address this, we modify the encoder to also output a single continuous confidence value for each representation type. This is then used to weight the mean, allowing for more confident views to have a greater impact on the basis feature, while also providing some interpretability to the model. Using this method, we are able to get 4 confidence values for each view: the confidence in head position, appearance, relative gaze, and the common features. Using this intermediate output, we are able to gauge the quality of the inputs without yet using any annotation. For example, whole head patches provide greater confidence for the head representation, while eye patches provide better confidence in relative gaze features. To evaluate our method, we conducted a variety of few-shot learning experiments using the EVE dataset. For the sake of time, we show here our main results comparing our basis loss model to the cross-encoder with and without the new feature representations. Our model improves on each baseline in all cases, regardless of the amount of final labeled training samples used. For further details and experiments, please see our paper. To summarize, we expanded on the cross-encoder paper by disentangling head rotation from relative gaze, as well as creating a more flexible, efficient, and performant model. We also introduced a measure of confidence, which allows the model to be interpretable even without annotation. All our code is available at the displayed link. Thank you for your time.